Hello everyone, I'm Dr. Karthika from Department of Biomedical Engineering, SNS College of Technology, Coimbatore. And in this May 2024 lecture series, previously we have discussed about sliding window filters part 1, and now we are going to discuss about sliding window filters part 2. Okay, in this part, while discussing about sliding window filters, we have to remind some features about digital image. First, a digital image is discrete in nature and the derivatives must be approximated by differences. We know that very well, and the first difference of the image G in the vertical direction for fixed I and in the horizontal direction for fixed J. For vertical we fix I, for horizontal it is J. N is a smaller integer, usually by 1. Here see the formulas del I and G of ij and del J G of ij. Del I G of ij, which is equal to G of ij minus G of I minus n comma j. Del J of G of ij, it is equal to G of ij minus G of I comma j minus n. The value n should be chosen small enough to provide a good approximation to the derivative, but large enough to neglect the unimportant ranges in the image function, because sliding window filters are used to remove the unwanted components in the image. See here, the gradient operators, it can be divided into 3 categories. The first one is operators approximating derivatives of the image function using differences, and we have rotationally invariant, example Laplacian, need one convolution mask only. Individual gradient operators that examine small local neighborhoods are in fact convolutions, and it can be expressed by convolution mask. Approximating the first derivatives use several masks. The orientation is estimated on the basis of the best matching of the several simple patterns. Operators which are able to detect each direction, each mask corresponds to a certain direction, because in previous video we have discussed about the edge detection, and in this edge detection we use and we consider both a magnitude and direction of the gradient. Same here. And the second thing is operators based on the zero crossing of the image function of the second derivative, and the third one is about operators which attempt to match an image function to an parametric model of the edges. Parametric models describe edges more precisely than simple edge magnitude and direction are much more computationally intensive. Here the categories of second and third will not be covered here, because I've made that as a separate part. First we have to discuss about the first category, because which is covered in our syllabus. And here first we have a Roberts operator. The magnitude of the edge is computed as h1, it is equal to 1 0 0 minus 1, h2 is 0 1 minus 1 0. The primary disadvantage of the Roberts operator is its high sensitivity to noise, because very few pixels are used to approximate the gradient, which gives high sensitivity to noise, because our filters which should be low sensitive to noise, then only we'll get the perfect clear output at the inside. Okay, and second one is Privet operator. In this Privet operator approximate the first derivative similarly to the Sobel, Krish, Robinson and some other operators that follow. And here the operators approximating the first derivative of an image function, and here the gradient is estimated in 8 possible directions, and larger masks are possible here. Here the direction of the gradient is given by the mask giving maximal response. Here we have the values of h1, h2 and h3 in terms of array function. And next one is Sobel operator. Here the values of h1, h2, h3 are represented here. Here it is mainly used as a simple detector of horizontality and verticality of edges, in which case only mask h1, h3 are used. If the H1 response is Y and the H3 response X, we might then derive H strength magnitude as root of x square plus y square or modulus x plus modulus y, and the direction as arctan y by x. Here we have a MATLAB program for example filter, and we have Robinson operator. The values of H1, H2, H3 are derived from the mathematical expressions, and also for Krish operator we have H1, H2, H3 values, which is also represented and derived from mathematical expressions. And in this image processing algorithms, we just going to use the arrays as mask. That's it. Okay, and while using non-linear image, we use certain filters. No, for non-linears, median is an order of the field. Median is an order filter. Here it uses order statistics. We know that. Given an n cross n window W of xy with pixel xy being the midpoint of W, the pixel intensity values of the pixel in W are ordered from smallest to the largest as follow: I1 less than or equal to I2 less than or equal to I3 less than or equal to up to in square. Here the values of W of xy and the median values are represented here. And while talking about linear, non-linear filters, we have to discuss about the morphological filter, because morphological filter is the main filter which is used in biomedical image processing to get true positive and true negative values of cancer and tumor imaging. Here we use the concept dilation erosion, opening which is equal to dilation erosion, and closing also used in erosion and dilation. Here the part, here the circle, it represents the morphological operation. Dilation and erosion means, for example, dilation means in this white background the pixels are represented in black. Erosion means black in white. Black in or else we can remember that in opening and closing functions. Opening means we have dilation and closing means we have erosion. Okay, based on the applications we can use either erosion or dilation concept. Dilation is used for black and white. If we take any cancer image like breast cancer image, means the cancer a tumor cell which is represented in terms of white pixels, which is called dilation. Suppose if it is vice versa, means it is erosion. Thank you. I think we'll get a clear understanding about sliding window filters, which is used in biomedical image processing as well as in general digital image processing. Thank you.